we have started for in the last 3 classes, we have been doing this module on digital modulation as part of this digital communication course. So, first in this module we have done baseband signal representation, baseband signal and baseband system representation in terms of their low pass equivalent signals and systems respectively. And in that context, we have seen that this is not baseband signal representation, but band pass signal representation in terms of baseband signals. So, we have seen that a band pass signal can be converted to a baseband signal by a process we called down conversion, and similarly it can be converted back to again the same band pass signal, and that process we called up conversion. And if we assume the low pass equivalent signals and systems of the practical band pass systems and signals, we have to take the signals as complex signals, because the low pass equivalent signal of a band pass signal is complex, and similarly same is true for systems also. And in the last 2 classes we have done pulse amplitude modulation, where we have seen that pulse amplitude modulation can be done in baseband as well as in passband. So, the only difference we observed is that the pulse that we take has to be baseband pulse, that is low pass pulse for baseband modulation, and a band pass pulse for passband modulation. So, we took examples like the baseband modulation. We can in fact get a passband pulse simply from a baseband pulse by modulating it by a carrier frequency sinusoid, so say cos omega ct. And then we have seen the importance of selecting pulse shape. Pulse shape actually dictates the spectrum that we are going to use, the shape of the spectrum that we are going to use. And in one class we have seen how to do demodulation for a particular example of rectangular pulse. We have from there we have seen that demodulation using the modulation using that pulse can be modulated signal can be demodulated using a filter and a sampler, and the filter impulse response can be taken as the same rectangular pulse. So, being motivated from that example, we have in fact considered a class of receivers where the impulse response of the receiver filter is taken to be the matched filter of the pulse that is coming to the receiver filter. So, we have seen that if these are the pulses, so if this is the diagram where xt is the transmitted signal and this is channel, this is noise, and here the signal is RT, the received at the receiver, and this is receiver filter AT, then this output is called YT, and this is sampled at every t capital T seconds. So, this here xt is summation of some scaled versions of scaled and shifted versions of Pu1t, the pulse, and the output here was called for Pu1t was called P2t, which is a convolution of Pu1t and Ct, and here the corresponding pulse when it goes here it is called P3t, which is P2t convolution AT. So, we have seen that if you take this AT to be same as P2 capital T minus small t, such a filter is called said to be matched to this pulse. So, if you take this particular filter, that particular filter we have taken, we have seen that we can demodulate the signal from this sampled values. So, at yk plus k plus 1 times capital T we will have something, we have seen that we will have ak times some constant plus noise term. So, from there we can estimate ak, this ak, which actually tells us what was transmitted at the transmitter. So, if we are able to detect this AK, able to estimate this AK, then we will be able to estimate the bits that were transmitted in that symbol also. So, then we have seen, if we take such a filter, if we take such a matched filter, we should actually sample at every t seconds, because that will give us the maximum SNR. There the P3T has the maximum amplitude, like we saw for two different examples. For rectangular, we saw that the P3T will have maximum amplitude here. So, this will give the maximum scaling of the symbol. So, the SNR, the noise is same, the signal is scaled maximum. So, it will give us maximum SNR. Similarly, for another example, for this pulse, triangular pulse, we have seen that this is P3T, again it is maximum at capital T. So, we have seen that sampling at every capital T seconds is the most beneficial in terms of SNR. Then we started proving that in fact out of all possible filters, matched filter is the best. So, in that direction, we have first characterized the SNR. We have seen that here this component y of capital T after sampling, this has two parts. One is contributed by the signal. So, A naught T, this part depends on A naught T. So, this part has some information about A naught T, whereas this part does not have any information about A naught. So, not A naught T, but A naught. So, this is simply noise. So, this is not desired, this is the desired part. So, we are interested in the energy of this part versus the energy of this part, expected energy of this part, because this is noise, this is random. So, SNR is the energy of this by expected energy of this. That is what is written here. So, that is how we have defined SNR, it is a natural definition, and then we wanted to maximize this quantity. So, we need to first calculate this. So, if we assume that noise is white Gaussian noise with power spectral density, two-sided power spectral density N0 by 2, we have seen that this variance is given by this. So, we have assumed that the power spectral density of the noise is N0 by 2, and then we have reached to this expression. So, this is the expected energy of the noise. Now, once we have that, we can now see what kind of filter AT will give us the maximum SNR. So, once we have this expression, what is the SNR? Our SNR is the signal energy by the noise energy. So, SNR is now signal energy by noise energy. Signal energy is simply mod square of this part So, where have we got this from? This is basically this YT. We have seen that this signal part is this. So, we can neglect this. A naught is actually, it does not depend on the filter. A naught is something which was transmitted. So, we can as well maximize this part, the energy of this part by energy of this part. So, energy of this part by energy of this part, we can maximize that. So, neglecting this part, we are seeing only this. So, energy of this is nothing but this. So, this is the energy of this part. And then expected energy of this we have just now, we have developed in the last class, we have derived it in the last class to be this. So, we have put it in the denominator. And now, we have a known inequality by it is called Cauchy-Schwarz inequality. The inequality says that if we have two signals G1t and G2t, both complex, maybe real also. Then this is, this holds minus infinity to infinity g1 star t g2 t dt square is less than equal to, so this is the product, take the integration and then take the mod square. Instead of doing this, if you take energy of each, then that will be bigger than this quantity. Energy of G1 is G1t mod square dt times energy of G2t is G2t dt. So this is the Cauchy-Schwarz inequality. So using this inequality, we can do something here. Take G1 to be P2 tau and G2 to be A capital T minus tau. Then what can we say? We can say that, using this, we can say that this square, this is just this part. So in fact, we have previously yes, A is P2, yes. So we take G1t to be, take A star of capital T minus tau and G2t to be P2t. Then check what is this? G1 star t. G1 star t is A capital T minus tau. So G1 star is, this star goes, because star conjugate of the conjugate is in the complex number itself. So A capital T minus tau, this is this, and then G2t is just P2t. So P2t times A capital T minus t, this is t. So we have basically this integration variable tau or t doesn't matter, because that is the integration dummy variable. So this side with this G1 and this G2 becomes this numerator, and then denominator, this part is in fact this part G1 mod G1t square integration, because mod A star or mod A are same things. So we have here, so using this we have Cauchy-Schwarz inequality tells us that P2 tau A t minus tau d tau whole square, this will be less than equal to minus infinity to infinity P2 tau d tau minus infinity to infinity A t minus tau d tau. We put A star or not, it does not matter, because when you take mod square it is the same thing. So now if we take this part on this side, we get this quantity by this quantity, that is this by minus infinity to infinity mod A t minus tau d tau. This is less than equal to this part. So now see the SNR formula. This is what we have got from Cauchy-Schwarz inequality using G1t equal to A star capital T minus T and G2t equal to P2t. So difference between this part and this part is just this factor, otherwise everything is same. So so if you put now n naught by 2 here, we can just divide this by n naught by 2. So 2 by n naught we can write. This part, this is less than or equal to this. And Cauchy-Schwarz inequality also says that this inequality will always hold, and this equality, this will be equality only if G1t is a constant multiple of G2t. So G1t will be, when G1t is just a constant multiple of G2t, then this equality hold, and that is the only case when this will be equality. Otherwise always it will be strictly inequality, strict inequality. So this equality will come only when G1t and G2t are essentially same except for a constant factor. So we have here from this, using Cauchy-Schwarz inequality, that SNR, this is the SNR, is less than or equal to 2 by n naught t, n naught, and root of minus infinity P2 tau squared d tau. Now what is this? This is the energy of P2. So this is 2 by n naught, the energy of P2. So that is, let us call it E, then it is 2 E by n naught. So SNR is less than or equal to 2 E by n naught. That is given, that results from using Cauchy-Schwarz inequality. Now when will this be equality? If this is equality, that is the maximum SNR. If it is possible to get it in equality, then that is the maximum value we can have. So when will this be equality? That is given by again Cauchy-Schwarz inequality, as we said. So what is the condition? G1t and G2t should be just constant multiple of each other. So that means our G1t was, if you remember, G1t is A star capital T minus T, and G2t is P2t. So if we say now G1t is some constant C times G2t, then so without loss of generality we can take just equality also, then also they will hold, the equality will hold. So what will that mean? A star T minus T is P2t. That will mean that A T is P2 star capital T minus T, and that's what is the matched filter. Okay. So here we have seen that we have first characterized the SNR. We have seen that SNR is always less than or equal to a maximum value 2 E by n naught, and equality, we achieve the equality only when G1t is a constant multiple of G2t. So instead of taking constant multiple, you can always take the constant as 1, and then we have taken one particular case, G1t equal to G2t, when we will have the maximum SNR. And that means we have seen that G1t equal to G2t meant that AT, that is the received filter, is matched filter, matched to P2. So we have seen here that matched filter maximizes SNR. That means matched filter is optimum. So we have seen that sampling, if you use a matched filter, previously we have seen that using a matched filter, it is best to sample at multiples of capital T seconds. And now we have seen that matched filter itself is the optimum filter, because that will give us the maximum SNR. Okay. So Now, in all this treatment, we have always taken only one pulse as input and analyzed what is happening, and using that we have seen what is the best filter to choose and what are the time instances when we should filter. All these things we have analyzed by taking only one pulse as input. We have not taken many pulses. Now, this may not give a generalized situation. This may actually create problem in practice, because in practice there are going to be more pulses sent one after another. So, what may happen is that the effect of a previously transmitted pulse may affect the reception of the next pulse, because the channel is not ideal filter. Channel has some response, and it may the pulse may spill over to the next symbol. Then they may overlap when they go through the channel, and then there will be some interference from the next symbol. Such a situation, such a phenomenon is called intersymbol interference, and presently we will see exactly how intersymbol interference really come into picture when you do this matched filter receiver or using any filter. So, the question we choose ultimately is how to choose this P1T, how to choose P1T, how to choose our receiver filter AT such that there is no intersymbol interference also. So, if we choose P1T, we will know P2T, because channel is fixed, we cannot change the channel, but when we receive it we can also design AT, and we have seen that AT should be actually P2 of capital T minus T. So, the only freedom we have actually is to design P1T. So, to design P1T, now we have to see that we should not have intersymbol interference. One symbol should not distort or should not disturb the detection of the next symbol. So, let us see. P2T we have seen is P1T convolution CT, and now we consider this transmitted signal, which is the transmitted signal for TM. Okay. So, previously we are taking only one term and analyzing the effect, what is happening at the receiver. Now, we will treat this whole input, we will take this whole input and see what is happening. So, Yt for this is Xt, then Yt is, again remember this diagram, this is not the, so we have this channel, then the noise, then the receiver filter. So, Yt is actually the convolution of Xt with channel impulse response and then plus noise, and then that convoluted with receiver filter. So, Xt convolution Ct plus Nt, this is the received signal, this is convolved with receiver filter impulse response At. Xt is this. So, if we put now Xt equal to this, what do we get? The summation can be taken outside. Instead of k, we put m as running variable. We will use k later, so we put m here. So, we have am, then P1 k t minus kt convolution Ct convolution At plus Nt convolution At. So, this is equal to Am P3T T minus Kt. So, remember P1T convolution Ct is P2t and that convolution AT is P3t. So when we have shifted here, the resulting output will also be shifted. So this is P3 t minus k capital T, and then the noise term remains NT convolution AT. Now we will be sampling this output at every capital T seconds. So let us see what is the kth sample. So the kth sample is ykt. So the kth sample is y of evaluated at ykt. Ykt is, so we have to take m here. This is we have replaced k by m. So here it is m. Here also this is m. Then now we are introducing k variable here. So kt, this is sampled at kt time. So this will now we place in place of small t we place k capital T. This convolution also evaluated at t equal to kt. So this is the sampled value at time kt. Now let us see what is happening in this term. What is there in this term? This am itself is a sequence, is a discrete time sequence. There is A0, A1, A2, A3. So if it started much before, it would have A minus 1, A minus 2, and so on. So there are these samples. These are also a discrete time signal, and this also as k varies, it is a this P3. So AM is a discrete time signal, and similarly P3 KT, capital T is constant, you are varying only K or M, let us say. So M or K, whatever. So this is also a discrete time sequence, discrete time signal. Now let us see what is the convolution of these two sequences. So this is the variable here is K, or you can have the same variable also, M or K, whatever. Let us use the same variable in both the places, P3 MT. Now if we convolve these two and take the value at K, what would we get? This, suppose this sequence is, we call this BM. So we are taking the convolution of these two. What is the convolution? Discrete time convolution of two discrete time sequences. So the convolution at K, suppose the convolution is CK. CK is M equal to minus infinity to infinity AM B K minus M. This is the discrete time convolution. Now in place of BM we put this, so B K minus M is AM, then P3, in place of M we put K minus M, so KT minus MT. So this is the convolution of these two sequences evaluated at the kth sample. So this term, whole term is a convolution. So this we can write as, this is AK convolution P3 KT. So this sequence and this sequence convolution, and take the kth sample of the convolution, plus call this signal N1 T, then n1 at kt. This is the sampled value at kt. Now this is equal to, take different values of k and we will write individually. So for k equal to 0, what do we get? So kt, so p3 of kt we get for, so this term is basically this term. So this term we will write for individual m. For m equal to k, what do we get? For m equal to k, we get ak, then p3 0, then plus other terms remain. M not equal to, we take m not equal to 0, m not equal to k, then am p3 kt minus mt plus n1 kt as it is. So we have just taken this this output at capital at k times capital T. There is a sampled value at kth sample, and this interval, this convolution is broken into two parts. One is m equal to 0, then the other is the rest of the values. Then we have ak times p3t, p30 plus this term. Now this term is the, gives us the kth symbol. So when we do this term actually gives us information about ak, but all these terms are effect of other symbols on this symbol. So we are going to actually detect ak from this sample, but what has happened is all the other terms also, all the other symbols are also interfering with this. So this term, this is noise. We have analyzed this and in the context of masked filtering, and we have seen that this we can do minimize the energy of this. We cannot really do, we cannot eliminate this. But this inter-symbol interference, can we eliminate this? So this is also undesired thing. So this is also undesired. This is actually inter-symbol interference. ISI. So we would like to avoid this term also. Okay. So from now on, P1t, P2t, all these terms will not come in this analysis. So we will have only P3t, one pulse, and we will denote that by GT. This will denote by GT. Then so we want the ISI term to be 0. We want so we are going to see what to do to ensure that the ISI is 0. So we have separated the ISI part from the signal part, the main symbol part, from which contains the information about the symbol, and we are going to see how to remove the ISI. So to say that all these terms are zeros, it means that this convolution has only one sample non-zero. All the other samples are zeros. So that means that so this is this convolution, yeah, this is not 0, but at the kth symbol, at the kth sample, we will have ak times p30 as the value. So that means we should have ak convolution g kt equal to ak times g0. So remember, this is a sequence, this is a sequence, this is also a sequence, but this is a constant. So this is really a sequence, a constant times the sequence ak. So when we do convolution of ak and gkt, these two sequences, we get a scalar multiple of ak. So that is what we want. So this will be true if and only if this sequence is the delta sequence, that is, it has only one non-zero value, that is the gkt So it is basically at k, this value will be k equal at k equal to 0, this value will be 1, and for all other k's it will be 0. So it will look like so g should be such that it is like this. So at 0 it has 1 value, and then it should come back to 0 at capital T minus capital T, and then it may have some other value, but at 2t again it has to be 0. So that is the restriction we are saying, that gt should be such a signal, such a pulse. So now this is the condition we need to ensure that ISI is 0. So this again means that gt, what is this sequence? This sequence is basically the sampled version of gt at capital multiples of capital T. So that means this is gt times this is equal to delta t. This is basically sampling, but the output signal is still represented in terms of continuous time signal. So this delta t minus kt, when this is multiplied to this, it will pick up only the value of gt at kt time. So this is this means this term, this expression. So that if we take now Fourier transform, what is the Fourier transform of this? It is, let us say, g of f, and this is product. So product will be convolution when we take Fourier transform. And what is the Fourier transform of this? Fourier transform of this is known to be again delta f minus m by t. So the fundamental frequency is, this is so there are deltas spaced 1 by t apart. 1 by t is a frequency, t is a time. So take at multiples of 1 by t frequency, there is a delta function. That is the Fourier transform of this. And what is the Fourier transform of delta t? This one. So now if we take the convolution, what is the convolution of gf and delta f minus m by t? It is g f minus m by t. These are all standard results from Fourier transform. This is one. So what does this mean? We have got that ISI is 0, ISI is 0 if and only if and only if summation m equal to minus infinity to infinity g of f minus m by t is 1. So this means, let us plot each of them and see what it means. Suppose we will plot each of these functions and then add all those functions for different m, then that should be 1. That is what it means. Now what is this function for m equal to 0? It is just gf. Suppose gf is something like this, and here is t. Then gf minus 1, this is gf minus 1 by t is basically a shifted version of this at 1 by t. So it will be like this. Again at minus t it will be like this. So we will have lot of these, and then when we add it should be 1. That is what it means. So we add these curves, it should give us this 1 value. So we have seen now what is the condition this pulse P3t should satisfy. Remember, GT is actually, we have used this as a different notation for this P3t itself. So GT should satisfy this condition. That means this its spectrum we should take, we should shift its spectrum at multiples of 1 by t frequency, and then we add those frequencies, it should give us a constant value 1. That is the condition for having 0 ISI. Now we told that we should actually see how to design P1t, because once we decide P1t, P2t is nothing but P1t convolution channel impulse response, which we do not have control on, and then P3t is nothing but convolution of P2t and AT. And what is AT? We saw that AT, the best AT is to take the filter matched to P2t. So AT also we have already decided that whatever is P2t we are going to choose a filter matched to that. So only thing we have to decide is P1t. So we should now take P1t in such a way that the overall this output pulse should satisfy this condition. It should satisfy the condition that you take the spectrum of P3t, you shift it by 1 by t, 2 by t and so on, and minus 1 by t, minus 2 by t and so on, and then you add all those different curves, different functions, add them, you should get a constant value 1 everywhere. So that is the condition for 0 ISI. Now let us see different cases when, how is it possible to achieve the 0 ISI, how to actually take P3t, how to construct P3t, what kind of spectrum GF should be, so that its shifted versions should add up to 1. So that we will see. So first suppose that GF has GF is band limited to B. It is band limited to, say, suppose band limited to frequency from minus B to plus B. That is GF is 0 for F greater than B and F less than B, less than minus B. So there is some B for which this will satisfy, but what may happen is B is infinity, that may also happen. So there is some B. Now case 1 is B less than 1 by 2t. That means what? That means you have 0 t, this is 1 by t, this is frequency axis, so 1 by t, 1 by 2t, 1 by 2 by t, this is 1 by 2t, this is minus 1 by 2t, this is minus 1 by t and so on. So this case says the GF is bandwidth is below 1 by 2t. So it is something like this. So when we shift it to 1 by t, what happens? What do we get? We get this. Similarly, we get on this side. So when we add this, are we going to get amplitude 1 everywhere? We are never going to get, because here there is nothing. So the value here will be 0. The addition is basically this. So it is not constant 1. So this case it is impossible to have 0 ISI. It is impossible to have 0 ISI for this case. Now let us see all the other cases. B equal to 1 by 2t. This is case 2. So B equal to 1 by 2t, here also what will happen is, in this case it is strictly less than 1 by 2t, but for equal to 1 by 2t, what will happen is these ends will touch, but there will be no overlap certainly. So the addition will be just in this section, the addition will be just itself, in this section the addition will be just itself. So for the addition to be 1 everywhere, this pulse itself should be 1 everywhere in this range. So the only possibility is, for 0 ISI is to have this GF. This is 1 by 2t, this is minus 1 by 2t. Then what will happen when you shift it to 1 by t, it will be like this. It will be like this. When you shift it to minus 1 by t, it will be like this. So it will give us constant 1 when you add all these. But if it is, if it was not like this, if it is like this, then we will get something like this, So it will not be 1. And also if it is more than, so if it is band limited to this, if the shape is otherwise, these shapes also will be the same shapes. So it will not be 1 everywhere. Now this is the second case. Now we have another case, that is B is greater than 1 by 2t. So case 3, B is greater than 1 by 2t. In this case, what may happen is that GF is, this is 1 by 2t, this is 1 by t. So it may be something like this, but when you shift it to this, it will overlap here. It will overlap here. But when we add these, this can be still 1. This can still be 1, even if they overlap. These things, this is decreasing, this is increasing, so they may add up to 1. So there are in fact numerous possibilities for this GF in this case. So numerous possibilities. And in the next class we will see that see a very standard pulse shape. In fact, we can, we will in the next class we will see that a very standard class of pulse shapes which fall in this category. So in this class, what have we done? We have completed the proof that matched filter is the optimum filter that will give us the maximum SNR for detecting the, so that will give us the maximum accuracy, minimum probability of error for detecting the pulse amplitude modulated signal. And then we have started seeing what is the pulse shape we should use. So here the idea is that for matched filter derivations we have used only one pulse transmission and checked what will be the SNR, what is the maximum SNR we can get. So there we have basically considered only noise. But when we transmit one after another symbols, one symbol when it goes through channel, its duration will elongate. So it will overlap with the next symbol. And as a result, this next symbol is getting distorted. So we will not be able to demodulate this symbol accurately. So this phenomenon is basically ISI, and we have seen how to design these pulses so that even if they overlap, we will have no ISI, no intersymbol interference. So we have derived this condition, and we have seen that the resulting pulse, that we should design P1T such that P3T should have a spectrum satisfying some condition. And that condition is that if you take the Fourier transform of P3T and then shift the spectrum by 1 by t and multiples of 1 by t and add all those spectrums, then we should get a constant amplitude of 1 everywhere. So its value should be 1, not only the amplitude, its value should be 1, that is phase is also 0. So that is the only way to get 0 ISI. But for this GF itself, this condition, to satisfy this condition, there are many possible pulses. There are numerous choices for P3T. We have seen 3 cases. One is the bandwidth of the P3T pulse is less than 1 by 2t, in which case it is not possible to satisfy that condition. It is equal to 1 by 2t, in which case there is only one choice, that is the rectangular pulse from minus 1 by 2t to 1 by 2t. And then we have seen that for B greater than 1 by 2t, there are numerous choices. We have not really found examples of such things, we will see in the next class, but we have discussed why intuitively it should be so, why it is possible in such a case to have different P3Ts which will satisfy that condition. So in the next class we will start with this raised cosine pulse, which I said falls in the case 3, and this is that pulse shape is very commonly used pulse shape, so it is a very important thing. And then we will start other modulation techniques, other generalized techniques than PAM. See you again in the next class.